Okay, so good morning. This is the last day of this series of lectures. And so today, so that's lectures, I guess, 9 and 10, I would like to give you an idea of what Tat did to solve the equation he had written for properly colored triangulations. Okay, so I'll start by recalling what we did last time, or some of the things we did last time. So we first wrote equations. So the first one was for the generating function of all planar maps. And they were counted, as always, by the edge number, the degree of the root vertex, the degree of the root face, also called outer degree, and they were weighted by their Tat polynomial in two variables, mu and nu. And so for this series, we wrote an equation with two of these catalytic variables. So I will just copy it. You probably have it in your notes already. So it was symmetric in x and y, mu and nu by duality. Mu x minus 1. And then came divided differences. And finally, a symmetric term. Yep. Okay. And so this equation was written by Tat in 1968. Okay. So another thing that we explained, that we did, was to relate this Tat polynomial to a coloring problem. And the connection was as follows. So for any graph, in fact, as my connection. Yeah. So if we look at the sum for any graph, if we look at all colorings of the vertices of the graph in Q colors, taken in 1, 2 up to Q, and we weight each coloring by some nu to the number of monochromatic edges in the coloring, then we get something that is actually a polynomial in Q and nu, and that is closely related to the Tat polynomial. Namely, the transformation was mu minus 1 times the number of connected components of the graph. So it's graph G, and we have mu minus 1 to the number of vertices of the graph. And then we had the Tat polynomial, mu and nu, and the connection between this mu and Q was that Q is the product mu minus 1, mu minus 1. So this told you, so this is also called the partition function of the Q-state Potts model. And in particular, when nu is 0, you recover here the chromatic polynomial, which counts all proper colorings. So those in which two neighbor vertices never get the same color. And I also mentioned that if you look at triangulations instead of general maps, you can write a similar looking equation, which we didn't write, but we only wrote it in the proper case, that is when nu is 0. And so that is for triangulations of a polygon properly colored. We wrote the following equation, also due to TAT. So we had the case of a single edge, which can be colored in q minus 1 ways. Then we had a proper product term. And another divided difference. So far there's no z, sorry. T squared x2 y and this is also due to TUT 5 years later. So these equations are roughly of the same type, the important point being that they are one quadratic. You have products of these two series, and that they involve divided differences with respect to the two variables, one with respect to x, one with respect to y. So this C2, I should tell you what it is. So C of xy can be expanded in y. And so this starts with 2. So somehow C2 is the first non-trivial term in this series. Are there questions on these equations so far? They should ring a bell. Sorry? They are not related. That's a generating function for all planar maps. And C, maybe I should write the definition, is the sum of all triangulation of a polygon. So you have T again to the edge number, x to the degree of the root vertex, y to the degree of the root face. And here you have the chromatic polynomial of T, that is the polynomial that counts proper coloring. So this sum when nu is 0 in other terms. Okay, so that's what we wrote last time. And I also told you of this very nice result by TAT, which is the solution of this equation for color triangulations. I think it's probably the third time I'm writing it in this series of lectures, but one never gets bored with it. So if you count, say, let's call it h of w, be the generating function of q colored triangulations of a diagon. So now you want the outer face to be 2, but in fact by deleting one edge, this is equivalent to requiring that the outer face has degree 3. And then we count them by vertices. So the connection with this series here So it's, if I'm not mistaken, 1 over W C2 of 1. So typically, in all such equations, what we are really interested in is the double specializations. So here you want somehow the first coefficient of the expansion in y, and you want to evaluate it when x is 1. And then he had this differential equation in W, C2 of 1. So I should tell you the connection between the variable t and W. So it's t is W cubed. So you always have this periodicity phenomenon, which makes, is that incorrect? Yeah, which makes the series periodic in some variables and not in the number of vertices variables. So the equation is second order, second degree. The derivatives are taken with respect to W, the vertex variable. And then comes a term that vanishes when you have 4 colors. Sorry? Oh no, there's no Q remains Q. And you're right, I'm rather puzzled with that. Yes, you're right. That's the right direction. Thank you. So then maybe this factor should be corrected. This has to be checked. Okay, so what happened is that Tat wrote this big equation for maps weighted by the Tat polynomial, couldn't really solve it, wrote a slightly simpler version for Q-colored triangulations. It's not much simpler. Maybe it's only the fact that here you have just 1 quadratic term instead of 2. I'm not sure it makes a huge difference. And then he struggled for 10 years to come to this differential equation, which, as I told you, is equivalent to a nice recurrence relation on the number of Q-colored triangulations. So today I want to give you an idea of how he got from this equation to that solution. And well, one of the reasons is that there is no other derivation at the moment of this equation. So maybe I should add that some years ago with Olivier Bernardi, we tried to apply what Tat did in this case to this bigger equation, and we could indeed do it. So we have a similar result. So I won't give you the equation, especially because it's big. Say the series T of 1, 1. So T of 1, 1, you forget about these degrees. And so you just weight each map by its that polynomial. Also satisfies well, a differential equation, right, but as we write it, it's an explicit system of nonlinear differential equations. Okay. So I try to give you the main ideas of going from here to there. So it's nothing especially simple. I beg you to ask questions. And one of the reasons is that, well, probably I still do not completely understand what Tut did and what we did, in a sense. I mean, I'm copying the details and have some sort of understanding, but there's certainly something better to be done. Okay, so this was my introduction. And now I would like to tell you that there is more in Tut's papers than this result of differential algebraicity, as we say. There are also, or hidden in his papers, are some algebraicity results. So some algebraic series are hiding in this problem, algebraicity, but it's only for some values of Q. Yep. Yes, it is, but that's a mistake. Thank you. Okay, so there are some signs that suggest that some special cases of this coloring problem should be algebraic. And here is one hint, which in fact doesn't deal with triangulations, but with general maps. If you take general planar maps and you just want to bicolor them properly, okay, so maybe okay. Here's one. So you have Q colors, so that's the case when Q is 2 and somehow nu is 0. So this problem is a special case up to this transformation of this general equation. Well, so in this case, if you want to solve this problem, you don't need this big equation, because you can, as we did in the first lecture, you can write an equation for this problem with a single catalytic variable. So these are also bicolored maps or bipartite maps with a coloring. So let me denote by B, like bicolored, bipartite of T and Y, or B of Y. The generating function of these bicolored maps counted by edges and by the outer degree, as usual. And now I just want to recycle for such maps my basic decomposition, which boils down to deleting the root edge and looking at what's left. And we'll see that this works very nicely. So what happens now that I'm entitled to use this board? I'll do it. So you have the initial case where you have just one vertex which can be colored in two different ways. So that's a 2. And then you have the isthmus case where the root edge is a bridge or an isthmus. So what do we get here? We have one additional edge. The outer degree gets a 2. And here, say to the right, we should take one rooted bicolored map, so that's a B of y. To the left, we should take another, but its root vertex should be of the other color. So I need to divide by 2 to avoid making this edge monochromatic. Okay, so far so good. And then we have the non-bridge case. So that's a map. So in this case, we delete the root edge. We just get this bean shape. And there are a number of vertices here on the outer face. And so say if the outer face is bicolored, so the outer degree is even, say 2D. And when you go backwards, you want to start an edge here and join it to one of these, say, white vertices. So this means in every other possible corner. So what you get is a sum over all these. Here you get the generating function of maps with outer degree 2D. And then what can you do? So you can, a loop is forbidden because this would create a monochromatic edge. So you can land here, which does not change the outer degree. Or you can land here or here, and then you get outer degree 2. So this is typical of those geometric sums that we had. So let me just rewrite this term. So what will you get? That's the sum of b to the 2d, y squared, y 2d minus 1 over y2 minus 1. And this series can be written watch b of y minus b of 1 over. Okay. Let me check if this fits with what I wrote. Yeah. Okay, for this problem, bicolored maps, we can write an equation with just one catalytic variable. So that's counting bipartite maps with a further weight 2. And this can be solved using our recipe, and the solution is algebraic. In fact, the coefficients are nice. Sorry? No, because so this B, so it's a sum over D of BD YD, but in fact the outer degree has to be even, so you can also write this as B2D Y2D, which is what you have here. Okay, and so you get this, in fact, well-known result. The number of properly bicolored maps with n edges, and this works when n is at least 1, is a bn e to the n plus 1. As always in those map problems, you have two linear terms at the denominator and the binomial coefficient. And the series B of Ty is algebraic. Okay. So that's one example of our very general problem, which yields an algebraic solution. Now I want to mention a second hint, this time for 3 colors. It's cheating because you'll see it's in fact the same example up to a bijection. If you take properly 3 colored triangulations, so now this is a special case of this problem when Q is 3. So we wrote a complicated equation for this problem, but in fact, it's equivalent to counting those properly bicolored maps. And the series, the generating function is algebraic. So let me take so I want to prove that the number of such colored triangulations is up to some factor equal to this number of bicolored maps with n edges. And so that's n plus 2, that's vertices. That's the number of vertices. And there's a factor. Where's my factor? So it should be 3 times p. Okay, so maybe I'll start from one of these bicolored maps that we've just counted. Or do I want to? That's the root corner. Okay, let me make it small. And I want, so it just uses 2 colors. And I want to transform it into a triangulation using 3 colors. Well, I just need to add a vertex in every face of the 3rd color and triangulate every face of the original map. So certainly I get a triangulation. It's properly 3-colored. So if I started from a map in which the root edge has colored, say, white, black, then I get a triangulation with the same property. So from this will come these factors. And the fact that I can go backwards, that is starting from a triangulation with a 3 coloring. So there's the 2 colors of the root edge, and I'm just deleting every vertex of the 3rd color. So regarding the weight, so say we started from white, black. So I get here that Bn, so that's just half of the bicolored maps, and I get, so you can count vertices and edges, so this tells you that you have n plus 2 vertices in the triangulation, and then I get just 1/6 of the bicolored, of the 3 colored triangulations, because again I fixed these 2 colors. So 3 choices for the first one and 2 choices for the second. Okay, so these 2 problems, they are in fact the same ones, except that one is stated in terms of 2 colorings and the other in terms of 3 colorings. So that's another algebraic case. And in fact, there are more. How do you want to state this? So maybe so that's not really written in Tutt's papers. You should combine this probably with my recipe paper with Arnaud Jehan. And there are similar results with Olivier Bernardi. So in the series of 10 papers that Tutt devoted to this equation, what he proved, or he proved special cases of this, if you take Q to be 4 times cosine of k pi over m, where k and m are integers, but you should avoid the extreme values. And in particular, so if you could take k to be 0, this would give q equal to 4. And if you could take this extreme value, m over 2, this would give you q equal to 0. So you have to exclude these 2 cosines. Then, so the series we are interested in, so that's the series that counts q colored, well, q is no longer an integer here, so it's triangulations weighted by their chromatic polynomial evaluated at this special algebraic value. Then this series, which now only involves 1 catalytic variable for the degree of the root vertex, it also satisfies an equation in 1, and I insist on the 1 catalytic variable. So this is the x. And so if you combine this with our general results, and you can see examples dealing with the more general problems in this paper by Bernardi, and so this series is algebraic. So for instance, so here are some interesting values. So since you want an integer between 0, so at least 1, so m should be at least 3, I guess. So if you take m equal to 3, k equal to 1, so you have q is 4 times cosine square of pi over 3, And I always need to make my little picture to see that this cosine is a half. So that's 1. Okay, so one-colored triangulations, there are very few. You need colors, not just one. So in this case, the series is 0, but indeed it is algebraic. So let's move a bit further. When m is 4, then you can take, again, k equal to 1. And then q is 4 cosine square of pi over 4. So that's 1 over square root 2. So it's 2. Here we get the bicolored case. But again, if you want to color a triangulation, well, it contains triangles. And so this is, in the case of triangulations, this is, again, a very degenerate case. Okay, so maybe let's move to 5. Then we can take 1 or 2 for k, and then you get some values of q that, well, maybe are not so exciting for you, but still, you know that the series, corresponding series, will be algebraic. And then another interesting case, and in fact the last case that gives an integral value to q is when m is 6. So you have pi over 6. The cosine is square root 3 over 2. And so these are the 3-colored triangulations, properly 3-colored triangulations, for which we've just explained that indeed their generating function is algebraic. And with Olivier, we proved a similar result for the map problem. So now for the bivariate third polynomial, so again, when q is 4 cosine square k pi over m with the same conditions, well, t of x1 satisfies an equation with one catalytic variable x and is algebraic. So I would bet that it's not algebraic. It's not known beyond the fact that this differential equation that I wrote down is a bit simpler, because the last term had a factor q minus 4. I'm essentially certain that it's transcendental. In terms of asymptotics, I think you can't see that it is not algebraic. That is, I think it has the usual asymptotic behavior of planar maps with minus 5 halves. Sorry? So you fix two integers, m and k, and you No, it's you. So for instance, you can choose M to be 6, K to be 1. Then this means that the number of colors is 3. And then you count all 3 colored planar maps or triangulations. So what I conclude, so in this case, this will mean, for instance, in the triangulation case, that if you take all triangulations, weight them by anything, say the edge number, and by their chromatic polynomial evaluated at this bizarre point, then this series, let me call it C of T, satisfies this algebraic. That is, you have an equation in T, a polynomial equation that vanishes. So that's what I mean by being algebraic. Are there more questions on these results? Okay, so this is, in a sense, this, well, not algebraicity because he didn't state it in those terms, but the existence of this equation in one catalytic variable, which will be explicit, is some intermediate step in Tutt's solution of this problem. And the rough idea is that if you know, in some sense, this series for all these values of Q, and there are many, 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 given that this series has just polynomial coefficients in Q, you're not far from knowing it for a generic value of Q. So what Tutt did is that, in fact, he established his differential equation for those values. Even though we know that the solution is algebraic, he wrote a differential equation, so something belonging to a more general class of series. And then he said, oh, if this equation holds for all these values of Q, then it holds for Q and indeterminate. Okay, so that's the idea. And so to tell you what Tutt did, I will try to apply his method to another problem, which is simpler because it's linear. And then I'll state the counterpart of these results for triangulations. So, yeah, sure. Yeah. I have no idea of that, but I know that these values of Q, they occur in many, many places. They are sometimes called the Tutt-Beraha values, usually when K is 1, but they have the same behavior. And so they seem to have lots and lots of properties in many contexts. Frankly, no. It's not a coincidence. I mean, something happens for these values to the chromatic polynomials, I think. Yeah. It cannot be. I mean, they occur in so many different contexts. There has to be something. Okay, so now I'll move to something that sounds completely different, another problem to which I want to apply Tutt's ideas. And this problem will be a problem of walks in a quadrant. As we saw last time, such problems were related to counting bipolar orientations of maps. So here's one more problem of walks in the quadrant, which was first studied by Germain Creveras in the 60s or 70s. It's been solved now several times, and I want to give one more solution based on Tud's ideas. So what is the problem? You take the quadrant, and you take lattice walks that consist of 3 steps: south, west, northeast. They start at the origin, and they have to stay in the quadrant. And so you define for them a generating function Q like quadrant, which involves a length variable, the length being the number of steps, and then 2 catalytic variables, x and y, which record the coordinates of the endpoint. So for instance, this walk here, diagonal, diagonal, south, diagonal, west, would contribute a monomial in my series equal to 1, 2, 3, 4, 1, 2, 3, 4, 5. And then the coordinates of the endpoint are 2 and 2. Okay? So that's a problem. We want to count such walks. So the first step will be to write a functional equation, which is always very simple to establish, involving these 2 catalytic variables. And in order to do so, we say that, well, a quadrant walk either is reduced to the starting point, length 0, coordinates 0, 0, or they are obtained by taking a walk and extending it in one of the 3 possible ways. So this adds a step and modifies the coordinates of the endpoint. In a way dictated by the 3 allowed steps. But of course, if we stop here, we've done some forbidden moves, which we will now subtract. So for instance, assume we ended here, then we're not allowed to add a south step. And so we should remove t over y, and the generating function of walks ending on the x-axis is this q of x0. And symmetrically, we should avoid ending on the y-axis and adding a west step. So I will use my favorite notation that x bar is 1 over x, and similarly for y. And then this equation can be rewritten if I put together all terms in q of xy. So this equation you should consider as the counterpart for this simple problem of the equation written for Q-colored triangulations. It's much simpler because it's linear, but still, it has two catalytic variables. Okay. So I told you last time about one way of addressing such questions involving the definition of two involutions and the finiteness of a certain group. It cannot be applied to this problem. So the group is finite, which is nice. It has cardinality 6. But when you take this alternating sum over the group, then you get 0 is equal to 0. So you've lost information, obviously. So this is harder than the cases that we looked at last time. So we have to do something different. And one different thing that we can do, is follow Tutt's ideas. So the first ingredient in the solution that I suggest here is to cancel what we call the kernel. What is a kernel? It's this polynomial here. By an appropriate choice of x. So this idea is very often called the kernel method. And now you have to keep an eye on what I'm doing, because in my notes I solved everything in y rather than x, so I will have a hard time with that. Okay, so this kernel, let me denote it k. So that's 1 minus t xy plus 1 over x plus 1 over y. And writing that k of xy is 0 is writing that, say, x is t times x squared y plus 1 plus x over y. So it's quadratic in x. You have two solutions that you can write explicitly with a square root. And so if you expand them in t, you have obviously one that starts with t, and then terms in t squared, and the other one starts with a term in 1 over t. So it's y bar over t plus bigger of 1. And so in general, x0 and x1, they are series in T. So I should say Lorentz series, since one of them has a negative power of T with rational coefficients in Y. So this Q is the rational, not the series. Okay, so now we have found these two series, x0, x1. What happens if we replace x by x0 in the equation? So the left-hand side vanishes, so the right-hand side must also vanish. And what you get, so if we specialize x to x0, which I recall depends on y, we get that this is 0. So maybe I should multiply by xy. You get x0 times y is equal to t y q of 0y plus t x naught q of x naught 0. Okay? So you get an equation for what is sometimes called the sections of this series. That is the values when x or y is 0. So this I will denote R of y. And given that you have this diagonal symmetry in the steps, you also have an xy symmetry in the series. So this is here, this is R of x naught. Okay, it's the same series by symmetry. So we've got an equation of a different type for this series, only involving now one catalytic variable. So the idea is that we'd like to do the same at x1. As you say. So certainly the kernel vanishes. But the problem is that this series, they are no longer defined when x is x1. Because, for instance, in Q, say, of xy, you have all these walks that just take diagonal steps. So you have a sum of t to the n, xn, yn, plus other terms. But each of these terms, if you replace x by x1, gives some t to the n, y to the n, and then y bar to the n over t to the n. So a series starting with 1. And then you're in trouble because you cannot have this is not a proper substitution. So this is often the case, but on this example, there's a way to remedy this, and it won't really stop us. So that's a little trick. Probably not the last trick. Well, no, because you'll have the same, you'll have the same trouble for this series here. So I don't think that the yeah, yeah, I don't know. So the trick is to move our variable x, sorry, I knew it would happen, a variable y around t plus some little o of t. And if you do that, then both roots x1 and x0 will be legally substituable, can be legally substituted for x in the series. So one choice that I like, but there are others, And you'll see later why I like this choice. Looks strange, but it has a nice symmetry property, although I have a root here. So again, my U bar is 1 over U. You could take, there are alternative choices like t plus u t squared and others, but this one is convenient for later. Then if you do that, then the two roots, well, they start with a term in 1 over square root t so you'll think, and they are, you obtain one from the other by replacing u by 1 over u. And so that's why I like this choice here. But both can be, say, legally substituted for x in Q of xy. And I'll try to convince you of that. So say that I consider one monomial, sorry, one monomial in this series with corresponding to a walk with n steps, and more precisely, A diagonal steps, B west steps, and C south steps. So the contribution in Q of xy of this walk will be t to the n, that is a plus b plus c, and then x, a minus b, y, a minus c. Okay, because this is the abscissa of the endpoint of my walk. Are you okay with that? Okay, so now if I look at Q of, say, x naught y, this will become t, at least at first order. X, we said it's u over square root t a minus b. And then y has been set to t. And there are correcting terms. So the power of t in that is t to the, so a to a minus a half, so that must be 3a over 2. The b is, and the c vanishes here. And then I've missed the power of u. I don't care so much about it. Okay. And so this exponent here, I thought is that correct, this exponent? I thought I was getting something, a larger power of, a larger factor of a. Yeah, just have a mistake here. So this is larger than what? So A must be larger than C. So this is plus C over 2, because as I end in the quadrant, A is larger than C. And so this is in particular larger than, say, n over 2, A plus B plus C over 2. So let me state it again. A walk of length n gives a contribution that starts with some t to the alpha, where alpha is at least n over 2. Which means that, if I state it backwards, I will get finitely, since there are finitely many walks of length at most n, I will get finitely monomials with a given power of t. And this is what is meant by being legally substituted. That's a good point. I hope it is. Could there be a sort of, yeah, yeah.
Still has a sense.
Yeah, but does the equations, I'm sure it does, and at worst you could, yeah, that's a point, but I'm sure it does. Otherwise it's horrible. I mean, that's the end of all our papers. Okay, so let me go back to this. So up to this little trick, writing y as t plus something and introducing a new variable u, which replaces y, we have found two roots of the kernel that we can both substitute for x in the equation. So this means that for both roots, we can write this. So let's write it. Okay, so we have, what do we have? Well, first, we have said that the kernel vanishes at x0 and xy and x1, yeah. And then we have written that r of x plus r of y and then the same thing for x1. And let me recall that what I mean by r of y is t y q of 0y. Okay? So good series with polynomial coefficients in q. Excuse me for a second. Well, you have more when you have 4, I'd say. But they are not so, I mean, it seems a bit artificial because let me remind that you just go from one to the other by replacing this variable u by 1 over u. So they are really, really equivalent. It's not more information. Okay, so this is, and maybe another way of answering your question would be to say that this equation by itself characterizes the series R. The other is very redundant in a sense. But still, let's keep the 4 equations. So that was the first idea. The kernel method cancel the kernel. And this is rather classical in such problems. The second idea, which is really the original point in Tutt's approach, is the notion of invariance. That's his terminology. So let's define this. We call an invariant any rational expression in what? In T, in X, and R of X that takes the same value at x1 and x0. Sorry? Sorry? At x1? Yeah. So that's the idea. Okay, so here, as we said, we have 4 equations with t, y. You write the variables that are involved here, t, y, x1, x0, and we have the values of R. And we also have R of y. Okay, so these are the variables that occur in these 4 rational or polynomial equations. So certainly, if from this collection of 4 equations, we eliminate y and R of y, so we eliminate 2 variables, and we get 2 equations between certainly t, x0, x1, R of x0, and R of x1. Okay? So maybe I can write one of them, for instance. So in the kernel, you just have the xi's and y. So if you eliminate y between k of x0, y is equal to 0, and k of x1, y equal to 0, you get something that I will write. You get that the products x0, x1 is t times x0 plus x1 plus x0 squared, x1 squared. Okay, so that's one of these 2 equations that relate these 4 or 5 quantities. I won't write the other. Well, I will write the other later. Okay. So if we get rid of y and r of y, we have two equations between these four things. So I say four because the t is always there. And the question is the following, and in fact it's some algebraic question, and I'm looking at Pierre because I have no algorithmic way of deciding this, and I think it's a well-posed question. So if you have, say, two polynomial equations between these four variables, can you decide if there exists rational functions in x and r of x, or that is in two of this series, that take the same value at x0 and x1? And in this case, by filling a little bit, you can realize that this polynomial equation can also be written as some I, like invariant of x1 is equal to I of x0, where I of x is the following rational function, t over x squared minus 1 over x minus tx. And so this I is an invariant. So let me say this in different words. We've restated the fact that x0, x1 cancel the kernel by saying that a certain rational function of x takes the same value at x1 and x0. Or rather, we've derived from this cancellation of the kernel the existence of some invariant, which only involves x, not r of x. And that's rather peculiar to this problem. Well, I should be careful. No, well, in fact, all quadrant problems with a finite group admit an invariant coming from the kernel like that. Okay, so that's one, and invariants do exist. And what happens for this Creveras problem is that we can build a second invariant. So far we've used these two equations. And now we want to build a second invariant starting from the other two. So again, we want to eliminate y and r of y. So eliminating r of y is something very easy. So from the other two equations, we get that r of x0 minus y x0 is r of x1 minus y x1. But we are not there yet because an invariant should be a rational function in x and r of x, but with no y. So we'd like to get rid of that. And this means that we would like to write y x0 minus y x1 as something in x0 minus the same something in x1. That is, we would like to decouple this term into a function of x0, a function of x1. But this is also possible. So if I get back to the equation k of x0 y equals 0, this means that 1 over t is equal to 1 over x naught plus 1 over y plus the product so yeah, I'm using.
It's not one of the two.
No, I'm using the all four equations here. So this tells you that y x naught is, so I'm just rewriting here the kernel equation, 1 minus 1 over y minus 1 over x naught. And of course, the same holds for x1. So getting back to this, minus y x naught, so these terms will be all over the place. It is on both sides. And so what I have obtained by playing with these equations is a second invariant, J, which I define to be R of x plus 1 over x. This is also an invariant. Yeah? Frankly, no, not that I know. And that's certainly a question. So as I said, if you look at all this classification of quadrant problems, for a finite group, the I always exists. That is an invariant that just involves x. And this one only exists in the 4 algebraic cases. But we have no, so really for the second one, the key condition is to be able to write this difference as a decoupled thing. And this just happens in those 4 algebraic cases. But we do not have any geometric description of why this should happen. No, in this case it is, but in some cases it will be first, it will not be a Laurent polynomial in x. Sometimes it will be a rational function of x with a denominator that has other poles, although the only poles that occur are at 0, 1, and minus 1, or something like that. Okay, so this problem, this quadrant problem, has this particular property that it has 2 invariants. And this is what is going to make it algebraic. Thanks to a simple lemma. I should check the time. So we have these 2 beasts, J and I. Use my pink color. So one is an explicit Laurent polynomial, and the other one involves the unknown series of x, which is essentially q of 0x. Okay, so the series we are after. And this lemma tells you that I of x must be a polynomial in the other invariant, j of x. So a polynomial with coefficients in y, with coefficients in, well, the series, say Laurent series in the variable. And I like to summarize this. So clearly, if you have an invariant, say this J, any power is still an invariant, takes the same value at x0 and x1. Any polynomial with coefficients only depending on t is again an invariant. So this gives you a collection of invariants. And this lemma, which is just stated in a particular case, comes from the fact that there are few invariants, somehow only polynomials in J. So here what I did, I've assumed that this lemma is correct, and I've identified this polynomial, first its degree and then its coefficients, by expanding this identity around x equal to 0. Okay? So if a polynomial exists, it has to be this one. But then I claim that this is just an equation in one catalytic variable for q of x0. What we have written is that I, so some explicit, what we have written is t over x squared minus 1 over x minus tx is equal to tj squared minus j minus 2t squared, you have 0, 0. Okay, and so I claim that this is an equation in q of x naught with one catalytic variable. You have something that is a polynomial in qx0, and you have this specialization that occurs here. So with our recipe, this tells you that this series here is algebraic. I won't give its value, but it has nice coefficients. And so I still need to prove the lemma. I had forgotten. So for the lemma, we're going to prove something a bit more general. Lemma. So we take a series in t and y that I write, I expand Tn yj times some coefficient ln j. And I want it to be an invariant, and in particular, this means that I should be, I'm back to y. So I want to be allowed to replace x by x0 and x1 in this series. And so the condition I will use here is that j should grow linearly, or even one, should grow at most linearly in n, with respect to n. So this is a series in T, power series in T. N is T0. With coefficients, so I want to start at 1. With polynomial coefficients in X. So let's consider such a series that is an invariant, so such that L of x0 and L of x1 coincides. So this is my usual shortcut. I do not denote the dependency in X. Well, then the conclusion is rather brutal. Then L is 0. That is, there is no invariant whose coefficients would be polynomials in X with no constant term. Okay? And so the connection with what I wrote here, the reason why it proves this lemma is that when I construct the difference here so, okay, maybe I don't know that this is 0, but at least this belongs to this ring of series in T with polynomial coefficients in X with no constant term. So I'm building this difference, and so it is still an invariant because it's a combination of invariants, and since its coefficients are now polynomials in X with no constant term, it has to be 0. Okay, so why do we have such a drastic statement? Why are there no invariants of this form? So you start from this. So you look, say, at L of x0. So this is the sum of Ln j t to the n. Then x0 is u over square root t to the j, and then you have smaller terms in t. So here this gives a term in t to the n minus j over 2, the first term here. So we want to look at the smallest exponent of t that occurs in this series. Okay, so let's define m to be the minimum of n minus j over 2 for the coefficients such that Ln j is not 0. Okay, so we assume that this L is non-zero, otherwise there's nothing to prove. So then, the first non-zero term in the expansion of L of x0, well, it will be this Tm times the sum over all pairs n and j, so that n minus j over 2 is m of Ljn u to the j. And by assumption, this is a non-zero polynomial because we have assumed here that one of these Ln j is not 0. Okay, but then, and I should add that j is at least 1. But then since L of x1 is equal to L of x0, this should also be t to the m times the sum over the same Lj, Jn. So this comes from replacing x by x1 now. You should remember that the difference between my roots, the x0 and x1, is that you replace u by 1 over u. So you have two series, and their initial term is a polynomial in u with no constant term. This one a polynomial in 1 over u with no constant term. So these polynomials have to be 0, and this contradicts my assumption. And so at the end you get that x has to be 0. There are no non-trivial invariants with polynomial coefficients. Okay, and that's why the simplicity of this argument is why I chose y to be of this form, t plus u bar t to the 5 halves. Yeah, yeah. So you have x1 of u is x0 of 1 over u. I mean, if I had not taken that, there would be different proofs. But it makes this proof simpler. Sorry? So this is, well, maybe, so this is not a precise statement. Probably the precise statement in this one. There is no non-trivial invariant, or so if I take an invariant with polynomial coefficients, it has to be independent of x, in other words. Okay, so I think that we have here all the pieces that yield from, so for this walk problem, from the equation in two catalytic variables to, over there, an equation in just one catalytic variable, implying algebraicity for this simple problem. That's just the first step, algebraicity. Then differential equations will come later. And so now I should tell you how this can be paralleled for the case of colored triangulations. Are there more questions on this solution for walks? So it works for those of you who are familiar with these quadrant problems. It works for all quadrant problems that have an algebraic solution. So it seems that their algebraicity is really related to the existence of two invariants. And so maybe I should insist to Pierre. So let me ask you directly. So this question, because at the moment we have nothing very clever for doing that. So if you have four polynomials, P1, P2, P3, P4, in variables, say x0, x1, and then R0, R1. Sorry, there's just two of them. So you have an ideal of polynomial. Can you decide if there exist rational functions in X and R such that this exists? As you can, in a sense, decouple this. So does it have an algebraic meaning in terms of this ideal of polynomials? But that's really what we are doing here. Okay, so back to maps, triangulations. this must be section 3. Algebraicity. And this time for colored triangulations. Okay, so now I start from this bigger equation. So what do I do instead of counting edges? This makes no big difference. I'm counting finite faces by a variable z. And the reason for that is just that I've been lazy, and as I did faces in the paper, I want to do faces again here. But this makes no difference. As soon as you control, say, the number of edges and the outer degree, and you know that you have a triangulation of a polygon, you can determine the number of vertices or the number of faces, and all these three quantities are equivalent. So then the equation for colored triangulations can be written like this. You have a kernel times your series, and it is equal to some right-hand side, so I'm trying to do things in a way that is reminiscent of what we had for quadrant walks. There must be a z as well. With k, so now it also involves the series C, so it's 1 minus xz over qy times c of 1y minus t, no more t, xz over y plus x squared yz over x minus 1. Okay, so that's that equation. So you have the main series, C of xy, times the kernel. And one big difference is that here, this series occurs in the kernel. Formerly, it was just a Laurent polynomial in x, y, and t. And you have a right-hand side involving two specializations of our series. And so one more thing that I want to do is to take out the factor q and then the factor y squared, introducing a new series, g, and we're going to work with g. The reason why I take this factor y2 out is that I want to write this as a specialization at 0. This is not a big deal. And so let me write this equation. I'll say this is a k twiddle because it won't be my k. So now the equation is k of xy, j of xy. So I've lost the factor q. So I have q minus 1x minus xz over y times g of x0 plus z and x squared y over x minus 1 times g of 1y. And now the kernel is 1 minus x y z g of y1 minus x z over y plus x squared y z over x minus 1. Yeah? You have a question? No. Okay, so I've just rewritten my equation. It's a bit more complicated than for the quadrant problem. So there are the same steps. The first one is that we want to cancel the kernel by some appropriate choice of x. Okay, so here is the kernel. So as you can see, it's not so bad because it's still quadratic in x. If you multiply out by this x minus 1, you get something of the degree 2. So it has two roots, which you could express with the radicals and this series in y inside. I won't do that. And again, if you want to make things, if you want to be able to replace x by both values, then you need to twiddle a little bit with the y. So there's one root rather clearly that starts with 1 and then big O of z. But then the other at first sight does not seem to be legally substituted in the series. So we have to fiddle a bit with the y variable. And this time I just take it to u times the size variable. So nu is the new variable. Okay, and then x1 will be big O of z. So if you look at this, the effect of taking y equal to uz is making this term big O of 1. Okay, and so clearly both are series in z, which can be legally substituted for x. And so both series, what do they belong to? So they are series in z, which is the size variable and has replaced t. And then the coefficients are rational functions in q and y. Okay, so we have two roots of the kernel. And this gives us 4 equations. So first we say that the kernel vanishes. That's how we've built these two series. And since they can be legally substituted for x, and the equation still holds, Philippe, for this series, fingers crossed, the right-hand side, which is here, must also vanish. So we get 2 more equations, the right-hand side, which is here. So we get q minus 1 xi for each I, minus xi z over y, g of xi naught plus z xi squared y over xi minus 1 times g of 1y is equal to 0 for both values of I, 0 and 1. Okay, and as you expect, the question is now from these 4 polynomial equations between x0, x1, g of x0, g of x1, y, g of y, y. So first we can certainly eliminate this one and the y. We get two polynomial equations between x1, x0, g of x1, and 0, g of x0, 0. So that's our 4 variables. Can we build from these 4 equations invariants? And this we'll discuss after lunch, I guess. Yeah. So if you have questions in the last few minutes, you're welcome.